Thanks for having me. Before I get started, let me tell you a bit more about myself. I am a software engineer at Flatiron. We are in healthcare tech. So we are building big data database for oncological research, and we work with cancer patient data. The company itself is based in New York, but I work for the Tokyo office. In Japan, we are facing a couple particular challenge. One of them is Japan has very strict data privacy law. So before we can send any of the patient data to our cloud database, we have to do depersonalization. And by that, we mean for any identifiers that can directly associate a patient, we have to remove all of it. So it could be a patient name, their uncle's name, their address. Right now, in our pipeline, we have people reviewing each of the document and manually redact the documents. So as you can imagine, this is a very time-consuming manual process. So what we would like to do is to convert these document scans into text data. And because we have access to these patients' information and structured data, then we can do a easily keyword search and remove these identifiers. But then, like I said, these are documents that have not been depersonalized. So we cannot use the more mature commercial OCR endpoints. And on top of that, we, in healthcare in general, we're facing data fragmentation issues. The source of our patient data can come from different systems. You can imagine like pathological lab, X-ray machines, they all have varying layouts and templates. So we're dealing with pretty complicated documents. Starting from around a year ago, my company started to look out for an OCR, an open source OCR solution to help us solve this problem. And just like a lot other machine learning technologies, we have seen a lot of developments in just the past year. And today I have some pretty exciting results to share. So today I share 3 open source OCR models that we found that outperform their peers, how we build a Python benchmarking pipeline to evaluate the models, and I also share the results and the trade-off across these OCR engines. So first, allow me to introduce the star of today's talk. Candidate engine number 1 is Paddle. So Paddle this year in May released a new deep learning framework, Paddle 3, along with an OCR toolkit on top of that. So this is a freshly baked framework and model. Right now, the support language, they support English and some of the major Asian languages. And this model is developed by the Chinese company Baidu. Candidate engine number 2 is called Yomitoku. So Yomitoku specializes in Japanese language, Japanese documents, and this was released last year in October. This is a fairly new project, relatively smaller in scale. And the third candidate is Tesseract. This is probably the most established OCR engines in the market. They've been around for quite a while and support a lot of languages. Yeah, so these are the 3 engines. Just out of curiosity, if we're doing sports betting today, can I see a show of hand which model you think would outperform the others? The 1, 2, or 3? Which one would you have guessed? I see a lot of 1. I see a couple of 3. Interesting. All right. And these are the metrics that we developed to evaluate the models. So first, we have quantitative metrics. Processing time matters to us. We do have a lot of documents, so speed matters. And the next thing is accuracy. So we decided to use the character error rate to evaluate how accurate the OCR result is. So for of all the contents, we see in the final result how many of the characters are missing, are added unnecessarily, or are converted incorrectly. So the lower the rate, the better it is. The lower the rate this is, the closer it is to the original content. And when we are trying to compare the results, the OCR results, we are facing a couple challenges. One of them is it requires a lot of normalization. So you can imagine, for example, a symbol, a comma. Different OCR models might convert them into different versions of a comma. It could be a half-width comma, a full-width comma, or an Arabic comma, which essentially mean the same thing, but they have different encodings. So when you're comparing the final result, you need to do a lot of normalization. And another challenge that we face is how are we going to create a scalable way to compare the final result with the ground truth? This is the algorithm that we came up in the end. What we will do is when we get the OCR results, so usually you will find a list of rectangle boxes with content in it. We locate the center line of the top leftmost, maybe it's easier to. We locate the center line of the top leftmost rectangle. And then from it, we take 10 pixel above and 10 pixel below. And then we find for the remaining rectangle boxes, we find all of the boxes that fall on this row and build the string this way. We use the same rule to build the ground truth. So this methodology is not perfect. Sometimes you would still see final results that they are flipped in order, for example, but they actually are converted correctly. And that's just, I think, one of the challenges that when you're working with non-deterministic systems. We have tried other more complicated algorithm. It turns out that the simpler version actually works the best. So we're using it. And then also the 20 pixel value, we also tried. We tried a 5, 10, and the 20 pixel width turned out to work the best for our situation. So that's the quantitative metrics. And for qualitative metrics, we're looking at, so OCR pipelines, usually they have two major parts. The first part would detect where exactly texts are, and the second part will convert the text. We compare the layout fidelity and see if these models can successfully locate where the texts are at. And also we take a look at the content difference and readability. One thing about language is some of the content, for example, logos, like a lot of the Japanese documents have like a seal. We care less about those content. So if an OCR model doesn't do a great job converting those content, we care less. And also when you just look at the error rate, that number alone, it sometimes doesn't tell you a very straightforward story about how readable the document is, to what extent the errors would impede your understanding. So we do like also take a look at the readability of the final result. And then in the end, I talk about developer experience. Okay, so this is the first image I'll share result with. So as you can see, this is a pathological report. It looks very similar to the kind of patient data that we are dealing with. Fairly complicated layout. There's a footer, there's a header. You can see some parts of the text, they are more sparsely located. We have, images and titles. So, drum beats. This is the result of this image. In terms of added distance, again, the lower the better. Yomitoku outperformed everything else. And then when it comes to processing time, Paddle is the fastest. And then image number 2, we have a report that's more complicated in terms of its layout. It has 2 panels, some form, images with subtitles. Let's also take a look. Again, Yomitoku, the smaller project trained with predominantly Japanese data, outperformed the other 2 models. And it's also the fastest. Oh, and in terms of the processing time, it's an average of 5 runs. And then for image number 3, this is an image that's relatively small and lower in resolution. It also, as you can see, have some handwriting in it. and the seal, for example, tricky layout. So let's take a look at the result. For this one, I think all three models struggle, and Yomitoku's error rate also increased for this document. Yeah, these are the quantitative results. And now let's take a look at the qualitative one. When it comes to layout, locating where exactly the texts are at, one of the issues that I noticed with Paddle is it has a tendency to fail to recognize texts when they are on the edge. It could be because when texts are on the edge, they are more likely to have distortions or slanting. But this is one of the patterns that we noticed when we analyzed the results converted by Paddle OCR. For Tesseract, the reason why it struggled with converting these documents, I think a lot of it come from it failed to just locate where the texts are at. You can see the green boxes. The green boxes are where the text is text, and especially for this one this part on the bottom, it just couldn't find a lot of the text. It could be because the texts are too small for the model, so you miss out on that part. And then when it comes to content differences and readability, so exactly what type of information these models got wrong with. When it comes to Paddle, the same issue. It struggles sometimes with content on the edge. Like for this document, it did manage to recognize where the texts are at, but somehow it still missed a lot of the characters. So for example, like this part is missing, and then these two characters on the edge of the lines, the model just failed to convert them. And another thing I thought really interesting is for Paddle, a lot of the mistakes come from converting kanji to a different version. For example, like in Japanese, this is kensa, 检查的检, and saibo, like 细胞的细. Sometimes it would use if it's a traditional character, it would use a simplified version, and sometimes it will use like a Chinese version of the same Japanese character. So these characters mean semantically the same thing, but they tend to mix up the versions of the kanji. So I think with that, in our use case, we do care about this because we need to do a keyword search, and these characters do have different encodings, so it wouldn't work for us. But if you're converting the document for a human to read, so it may not be creating as much an issue. So even though some of the error rate is high for of Paddle's result, I think the final converted text is more readable than you probably think. And then for Yomitoku, it does a very good job in general, struggles sometimes with logo and handwriting, and also when data quality is especially low. Okay, next, as we know, for OCR technologies, image quality matters. So we applied a couple techniques to help improve the quality of the image and see if it helped reduce the error rate. So the first method I'm using here is sharpen. It's a pretty simple algorithm. We apply a kernel. So for each of the pixel, if it falls on the edge, so it will the pixel itself. We subtract the color index from the surrounding pixel from the pixel itself. So if it falls on the edge, its surrounding pixels are significantly lighter, have the lighter color, that pixel alone will be more pronounced. And then with that, we create a sharper edge for the documents. I also tried to create more contrast in the image. For this algorithm, what we're doing is we extract the lightness value of a pixel. And then from it, you create a histogram. So for example, the x-axis is how light, like the lightness index. And then the y-axis is how many pixels of this image have that value. So you create this histogram, and then what you do is you like imagine like a pull both ends and then make these pixels fall more evenly on this range of lightness value. So what will happen is for the dark part of the image, it will become darker, and then for bright part of the image, it will become brighter. And then with that, we create more contrast in the image. So you can see, error rate got improved with both techniques. We have tried other ways, for example, denoising. The issue with removing noises in the image is it's harder to create a more generic solution for different kinds of image. Like with different processing, there are different kinds of noise. So we see less of an obvious like improvement across different images that we tried. Okay. Next, in terms of developer experience, I had no problem installing, setting up any of these models. Oh, yeah, I think I didn't mention. Tesseract, if you remember, is significantly slower than the other models because it doesn't have GPU support. And because of that, I'm giving it a 2-star for, for having no GPU support. But not every server has GPU, and it's more expensive. So maybe it wouldn't matter for your team. And then for documentation quality, Yomitoku, they're decent. All three models are decent. Paddle improved a lot, especially Paddle 3. Improved a lot in terms of documentation. Yomitoku in general doesn't have a lot of information. We think from the documentation, we don't really know what like deep learning architecture to use, what's the source of data. So I'm giving it a 2-star here. In terms of the output for downstream processing, our team, we care about two things. One is for these OCR pipelines, we want to have transparent outcome for each of the middle steps. So some of these pipeline would, for example, if it's a tilted image, they will like adjust the angle of the image. They also will create, for example, images showing like the detected text. We want to see like transparent result from every single middle step. For that, I think Paddle and Yomitoku does a pretty good job, especially Yomitoku, it give a confidence rate for text detection as well. And for all the other models, they just give you one confidence rate, could be just the text conversion confidence rate. That I found very helpful. And then for Tesseract, it creates this legacy format called HOCR. I personally don't find it very easy to use. You have to apply additional styling in order to render this in a browser. It's essentially HTML. And then also for our use case, we would like to have easy to parse text position and content pairing. For this, I find Tesseract's output a little bit too granular. So they break things down to the token level. So like you might have like one character with one pairing box, and you have to like piece everything together. For me, their output is a bit too granular, but of course, at the same time, it gives you more control. So the summary. I would say Yomitoku is the pretty obvious winner of this contest. In general, it does a very good job, consistently create production-ready text extraction. Even with, some of the documents we try to have very complicated layout. And also it's very fast in terms of processing. Sometimes it can struggle with poor handwriting. But at the same time, the kind of documents we have, like doctors are not known for having the best handwriting. And I think even humans would struggle with that. And sometimes like with the seal, with the logo, Yomitoku have some struggle converting the text correctly, but we don't care that much about those contents. it does have limited language support, Japanese only, and does read English as well. In terms of the licensing, it does not guarantee commercial use. Paddle, in general, does a good job. We, because due to time constraint, we tried actually more documents. With the simpler documents, for example, like this one, Paddle does a very good job. It struggles sometimes when it comes to documents with more complicated layout. But if your document is simple, straightforward, with consistent like chunks of text, I think Paddle is pretty good for that. And then at the same time, if you don't care about Paddle converting to the wrong version of the kanji, it's like the final result is pretty readable. Yeah, and it has like open licensing, allows unrestricted commercial use. Language coverage, Paddle 3 right now does not have a very wide language support, but more supportive language that they're coming out. For Tesseract, I'm not going to talk too much about. So like in general, we notice it's like struggle with a lot of the documents that we have fed it. Yeah, for some simpler documents, Tesseract does a fairly decent job, but Yomitoku and Paddle, they just did much better. Yeah. Okay, I think that's it for the talk.
Okay, thanks for being. And now we have the Slido's questions, and let's go. Okay, the first one. When using OCR to detect medical documents, is it necessary to mask personal or basic information? If so, what technologies are used?
If we're going to use this OCR, we'll just host it in our own server that lives within the hospital network. So there's no problem about that for hospitals.
Okay. While detecting medical documents, do you have any recommended tips to speed up the process?
It depends, I think, on where, like at what format you're saving the documents. We originally saved the content as like physical files, and then we found a lot of like overheading for I/O. And then now we save all the data in the database, which speed up the retrieval of the information significantly more. Yeah. And in terms of, and yeah, like if you care about speed, like I said, Tesseract does not have GPU support. Use GPU, obviously, it will speed up the process. Yeah.
Okay, next one. Do you use super resolution to increase image resolution to improve success rate, or it will only increase processing time?
Super.
Yeah. 提问者有在现场吗？
Oh, just to help improve the resolution of an image?
Yes.
It's like a library?
It's some technology to increase the image.
I'm not a computational like imaging expert. I'll look into it. Yeah. But I imagine if you have like better resolution of an image, I imagine the result will be better. Yeah.
Okay. In terms of signature recognition, do you have any recommended methods or tools?
Signature, like people's signature?
Yes.
That. I feel like it also depends on the culture. In Japan, people sometimes try to sign like more clearly, but in the US, for example, it's not supposed to be recognizable, I feel like. No, I don't. It will probably be very hard. If you want to if your purpose is not to read what the name is and to compare their two signatures if they come from the same person, I think it might be a different technology you're looking at.
Okay, next one. Since most models struggle with complex documents, did you experiment with splitting those documents into smaller parts and compare the performance?
Yes, we actually have done that. I don't have the data with me, but usually forms and text with like more sparsely located text, the models struggle with. But if you just give it a paragraph, a consistent paragraph, it does a very good job.
If an image source has stance, what other methods can be used apart from sharpening and adjusting contrast?
Mostly denoising will probably be one of the options. Like there are different kinds of noise like due to different processing in the image. So if your image tend to have or process the similar way, tend to have the similar kinds of noise, you might be able to find like one denoise algorithm that works particularly well with your type of image. Yeah, but yeah, for us, like what I said, like we work with different hospitals and the source of the image come from all sorts of places. So it's harder to find a clear pattern, like how to, at least we have not been able to find, but we are also not computational image like experts. That's probably the next step we'll look into it.
Okay. Since we have only 3 minutes to the session end, we will have only give question to the Slido. If you have any questions, you can discuss with the speaker after session ends outside the room. Okay. Next one. Would you consider fine-tuning paddle for the medical document layout and content?
We have considered this. It's more of a, like, we think the hospitals are okay with it because the document does not leave the environment, but it's more of a compliance issue we need to talk to the hospital about. But we have thought about doing that.
Have you thought about or explored using a combination of multiple models, routing a request to process an image with one model for one use case for another?
Yes, we have also. We are at a fairly early, like exploring stage. But in terms of the types of documents, for example, if one model works particularly well with radiological report we might use that for one type of documents. And some models would output like middle step output. Like if a model, for example, does a great job recognizing text and then another does a great job converting text, we're also thinking maybe we can chain up these two steps together.
What is the minimum number of samples required to achieve reliable performance for these OCR models? The amount of training data in your experience?
We're not fine-tuning the models. So if you're talking about the minimum numbers of samples, I think it depends on your use context, how tolerate of error rate you have. For us, we probably will still have a human component in it, so we're pretty tolerate in terms of error rate. We have not considered like how many exact documents that we are going to try. Again, like we're at fairly early exploration stage. Yeah. Oh, and another, I think, challenge is you need to create for each new documents you add to benchmark these models. You do need to build the ground truth of that. It's a pretty time-consuming process. We're thinking about reverse the process. So we will have text first and then create the image based on the text. so that we have ground truth to compare the converted result with. But we are worried it might not be a very authentic, like genuine documents that we create from text first and then image, and then we convert it back to text, see how well these models do. But that could be one of the easy ways to create large amount of test documents.
Okay, since the time is up, we can discuss with the speaker on the Slido and outside the
Can I say
room.
one more thing? We also tried easy OCR. Because I don't have a lot of time, I did not mention that. But easy OCR has a wide supportive range of languages, and that is also another engine that does a very good job. If you are interested in using that, converting documents as a non-Asian language, you can also look into easy OCR.